Okay, it's 2 minutes after 1. Let's go ahead and get started. Welcome everyone to MHPN's April webinar. My name is Xiaohanbao Smith. I will be your moderator today, and we're going to hear about the Beacon of Hope, the restoration project of the St. Joseph Church in Detroit. And before I turn it over to our speaker, I would like to go over some Zoom items. If you have any questions, please type them into the Q&A box as you think of them. All the questions will be answered at the end of the presentation. And the chat box will be used to share links or resources discussed during the webinar. Both the chat box and Q&A box are located at the bottom of your Zoom screen. If you don't see them, please wiggle your mouse and they should pop up. If this is your first time attending our webinar, we are the Michigan Historic Preservation Network. We support the sustainability and economic viability of Michigan's historic places through advocacy, education, and direct action. We could not do the work we do without our members and volunteers. If you're not a member yet, please consider joining us at www.mhpn.org. We have a quick announcement that our 2026-2027 Historic Resource Council directory is available online, and we will share this link in the chat in a bit here. Our directory members include archaeologists, architects, engineers, general contractors, trades contractors, consultants, developers, preservation organizations, and many others. It's a very useful tool, so please make sure to check it out. If you are seeking AICP credits, you will need to log in your credits online after this event using this link. I will send this information in the chat in a bit. And if you are seeking AIA credits, please send me your name and AIA number after this event, and I will log that credit in for you. So I will also share my email in the chat. Our webinar series are supported in part by an award from the Michigan Arts and Culture Council and National Endowment for the Arts. We want to say a big thank you to our sponsors. And it is my great pleasure today to introduce you our speaker, Julie Jones. She's a senior associate at West Jenny Elster Associates, and her bio is available on our website. I will send the link in the chat box too. And with that, I am going to turn it over to Julie.
Thank you, Jiaban. And let me get my screen up here. And thank you to MHPN for
Oh, Julie, I think your audio is I can't hear you.
Can you hear me now?
Oh, yes.
Okay, sorry about that. Thank you, Xiaoban. Thank you, MHPN, for inviting me to come and speak today. Again, my name's Julie Jones. I'm a senior associate at WJE, and I am here to talk about an ongoing project at St. Joseph Shrine, specifically the bell tower at St. Joseph Shrine, which the parish has dubbed the Beacon of Hope. And so that is also the name of my presentation. Here are our learning objectives today. In addition to all this, I really hope to share some of the most interesting nuggets that we've uncovered as a project team as we've worked through some of these interesting problems. And here is our game plan for our discussion. We'll start by talking a little bit about the history of St. Joseph Shrine. Then we'll dive into some masonry construction basics that are related specifically to our project. Then we'll go into some of the masonry deterioration that we've observed, and we'll get into some of the nitty-gritty of the repair issues and examples that we've worked through today. So let's start by talking about St. Joseph Shrine. This was originally established as a German Catholic parish in 1855, and originally it was called St. Joseph Church. The current church building construction began around 1870, and in these photos here, we can see a model of the current church building on the left, and in the right, we can see an image of the original construction team, including some of the stones that we are working with today. The Gothic Revival Church was designed by a German-born architect whose name is Franz Georg Himpler. The exterior walls of the church are constructed from Berea sandstone and dolomitic limestone. The steep sloped roofs on the church consist of slate tiles and of copper sheet metal. Here we see some images of a ticket for the original consecration of the new church building back in 1873. The original bell tower steeple was completed slightly after the original church building, more in the 1890s. And the church is located between the Eastern Market and Lafayette Park neighborhoods in Detroit. I really like the photo on the right, which is taken from what is now the DeQuinder Cut. So you can see in the foreground of the photo the railroad tracks that were originally there, and then in the background you can see our beacon of hope. The building was added to the National Register of Historic Places in 1972, which is about the time of this photo. In the early 2000s, the Detroit Catholic population was declining, and the St. Joseph Parish was down to about 50 members. In 2016, the Institute of Christ the King Sovereign Priest became involved in the community. And since then, the parish has grown significantly and really come together as a community to restore the church building, including the bell tower. Many of our colleagues in the Detroit area have been involved in these restoration projects. For example, Quinn Evans and Chris Min recently helped the parish work through and develop master plans for the community as a whole. Some of the enclosure contractors that have been involved are Detroit Cornice and Slate, Shana Roofing, Ram Construction, and Grunwell Cashero. These, as well as others, have contributed significant improvements to the building over the past 10 years. I really like these photos that I got from the Shrine Facebook page because you can see the stark contrast between this beautiful celebration happening in the community and the very unesthetically pleasing construction equipment in the background. It's remarkable how much this parish has done to really embrace this project. So now that we know a bit about the church and the community, let's talk about the project. The bell tower at St. Joseph is a historic mass masonry structure. What does that mean? Masonry walls can be classified in a number of different ways, including load-bearing, non-load-bearing, mass, cavity, multi-wythe or single-wythe, and reinforced or unreinforced. In the example on the left, we see a mass masonry wall. In the image on the center, we see a composite or transitional wall, and on the right, we see a cavity wall. Mass walls are the oldest and the simplest form of construction and rely on their thickness to bear loads and manage moisture. Transitional walls incorporate steel into the masonry and allow for the construction of taller structures with thinner walls. And then cavity walls include an airspace between the outer masonry and the inner structure to manage water. To understand how masonry walls can fail and how to repair them, it's important that we understand how the wall performs from both a structural and a water management standpoint. It's also important to understand the properties and functions of the actual materials that make up the mass masonry wall. Exterior walls of masonry buildings constructed prior to the early 20th century, such as St. Joseph Church, are generally characterized as multi-wythe mass masonry. Mass masonry walls are generally 12 inches or greater in depth. The exterior decorative white consists of brick, stone, terracotta, or a combination thereof, which are set integrally with the masonry backup, which consists of brick, stone, or an extruded clay tile system. Typically, the interior finish consists of a painted gypsum-based plaster that's applied to the inside face of the interior withe. The withes are generally interconnected using a header unit that's laid perpendicular to the typical coursing. Historic mass masonry walls can be load-bearing or can be a combination of load-bearing and non-load-bearing, like what we have at the bell tower. Load-bearing walls carry the structural gravity and lateral loads down to the foundations. Non-load-bearing walls have a structural frame that supports the floor and roof loads while the wall carries its own weight. Load-bearing masonry walls do not typically contain steel or wood members, and the walls provide support for the floor and roof members down to the foundation. The walls consist of a combination of various masonry types to make up a thicker assembly compared to like a transitional wall. These structures typically rely on compressive strength to resist gravity loads and the mass and width of the wall to resist lateral loads. Since unreinforced masonry are much stronger in compression than tension, arches and bolts were usually used to span openings. I like this photo, which is of the interior bell tower walls at the fourth level. There's no interior plaster, so the interior withe is exposed. And you can see here that we have no structural columns at this level. You can see here also that there are arches present at the window openings. And at the window openings, you can actually see the thickness of the walls. Mass masonry walls do not have a drainage cavity behind that outer withe to manage water. Instead, they store moisture that penetrates the walls during a rain event. Then the moisture within the walls evaporates from the wall faces. This is illustrated with these two graphics shown. On the left, we can see precipitation, hopefully if you squint, and the accumulation of water within the mortar between the masonry units. In the image on the right, we see evaporation of that accumulated moisture from within the wall. Mass masonry walls rely on a combination of surface shedding and wall thickness to resist water penetration. It's expected that most of the water will be deflected at the exterior surface with intact masonry units and joints, but some water will penetrate the exterior surface. Mass walls absorb, store, and then release moisture. Water leakage doesn't typically occur unless the wall becomes critically saturated, or if there are avenues for water to move more quickly through the wall, such as cracks or voids. The critical level of saturation is going to depend on the type and the condition of the wall assembly. One of my colleagues likes to compare mass masonry to sponges, which absorb and then release water. Since mass masonry assemblies rely on their storage capacity to manage water that bypasses that exterior masonry surface, voids in these assemblies needs to be minimized to prevent water from readily flowing to the interior and to maximize that storage capacity. For example, middle and interior withes of multi-withe walls should be free of large voids, and collar joints where present need to be filled. And then if plaster is present at the interior, it should generally remain intact. Here you can see a few photos of voids that we observed and addressed within the walls at the bell tower. So on the left, hopefully you can see a thin yellow wire, which was used to determine the depth of the void that was present within a joint between these two sandstone units. So we inserted the wire, pulled it out, and then measured the depth, which was almost 10 inches in this location. The center photo is a picture of Andreas, who is pointing voids in the brick backup wall. And then on the right, we can see a photo of a newly pointed brick backup wall. So now that we've established the definition of a mass masonry wall, here are a list of some common materials that we use in masonry construction. At our bell tower project, we've uncovered brick and two types of dimension stone that were part of the original construction. And here in this photo, you can see a simple little experiment that I did with my kids in the backyard. We took a couple samples one from the original finials and one from a finial that was recently replaced to help us determine the stone composition. The original stone, which is on the left, is sandstone and does not visibly react with the vinegar solution in the glass. The replacement stone, which is on the right, fizzes when it's submerged in vinegar, indicating that it's limestone. Sandstone and limestone can sometimes appear very similar. Okay, so let's talk some more about the original masonry materials at St. Joseph's Shrine. Brick. Brick is made from clay or shale, which are composed of silica, alumina, and metal oxides. Clay is formed, dried, and fired into a ceramic product. Colors are generally the result of minerals in the clay, although coatings can be used. The manufacturing process has 6 phases: mining and storage of raw materials, preparing raw materials, forming the bricks, drying, firing and cooling, and then dehacking and storing the finished products. At the bell tower, common brick is used as a backup material in many locations and is visible at the interior where it's exposed. In these photos, we can see brick masonry at the belfry level and at the 6th floor level at the interior. And even though these bricks are not an exterior exposed masonry type at the bell tower, deterioration is visible and indicative of issues that are happening at the exterior. So in the photo on the right, we can very obviously see water staining and efflorescence. Dolomite limestone. Dolomite limestone is one of the 2-dimension stones present at the bell tower. Unlike limestones, which are made of calcium carbonate, dolomite is a calcium magnesium carbonate. So when calcite is the dominant material, the rock is called limestone. When dolomite is the predominant material, the rock is called dolostone. It's now believed that dolostone forms when magnesium-rich seawater filters through limestone and replaces some of the calcium. This process was more predominant historically, so most dolomite is from the Precambrian era, meaning that it's over 500 million years old. Dolomite is used pretty extensively as a commercial limestone and is classified as a limestone in the dimension stone industry and is quarried in pretty large quantities. The grain size can vary between different dolomites, but all have a dense, sugary texture and a rib-like bed structure. Dolomite exhibits a great weathering resistance and hardness, which makes it very durable in exterior applications. Here we have some images of dolomite at the bell tower. The left shows existing dolomite, which is typically in the field of the wall. And then on the right, we can see a sample of the dolomite, which we are using for replacement units. Okay, let's talk about sandstone. This is the 2nd type of dimension stone at the bell tower. Sandstone is a classic sedimentary rock composed of grains of sand, such as quartz, which are cemented together by another mineral, such as silica. Prior to the formation of the rock, the sands within sandstone were transported by wind, water, or ice, which impact the shape of the grains. The color of different sandstones is influenced by the cement material binding the grains. At St. Joseph's Shrine, the sandstone is Boreas sandstone in a Birmingham buff color, which contains predominantly quartz grains and silica cement. Sandstone is used at decorative ornamental pieces of stone and as trim stone at like water tables, corners, and openings. So before we move on to our last material, let's take just one more moment to talk about sedimentary rocks. Sedimentary rocks, such as limestone and sandstone, are made from the sediment of loose material that's gradually consolidated and turned into stone over millions of years. These layers of sediment are called strata or beds and are the most common characteristic of sedimentary rocks. Separating these strata are bedding planes, which are flat surfaces along which these rocks tend to break. Changes in grain size or in sediment composition creates these bedding planes. Most strata or beds are originally deposited in horizontal layers. However, cross bedding can occur, which creates layers that are inclined to the horizontal. Since bedding planes are known to be more vulnerable to splitting and cracking, it's advantageous to consider bedding plane orientation when using sedimentary rocks in building construction. For example, if a mass masonry wall with sedimentary rock will be supporting its own gravity load applied in the downward direction, the stone will perform best if the bedding plane is set in the horizontal direction. This will help reduce the load applied between those bedding planes. Unfortunately, many of the stone units at St. Joseph's Shrine Bell Tower were originally set with bedding planes parallel to the applied load paths, which is sometimes referred to as face bedding. This is actually a common condition that we see, but this may have been the result of quarrying, sourcing, size limitations, or to reduce waste for cost purposes. Okay, the last material I want to discuss is mortar. Mortar of various compositions have been used for thousands of years. Mortar is the component that the masonry units are bed in, creating mortar joints between the units. Mortar accounts for less than 10% of the volume of a typical masonry wall, yet its influence on performance and aesthetic is pretty significant. For example, mortar holds the masonry units together to allow the wall system to act structurally monolithic. Mortar accommodates tolerances of the masonry units to allow for a more uniform installation. Mortar limits water infiltration between units. Mortar needs to be designed correctly, installed properly, and well maintained. Otherwise, cracks in the mortar or separation between mortar and stone will allow for water penetration. And finally, mortar accommodates incidental movements of the building and between individual units. Mortar affects the durability of the mortar itself and the unit masonry. Selecting the right mortar is critical to long-term performance. A common misconception regarding mortar is that harder mortar is actually better. In fact, not only is this false, but when mortar is harder than the adjacent masonry, the mortar can actually damage masonry units and reduce the wall's long-term performance and durability. If the mortar is too hard, the edges of the stone or brick in contact with the mortar can debond or even break as the wall expands and contracts with changes in temperature. Mortar must be compatible with the masonry and have some flexibility or softness to accommodate movement while still maintaining that bond with the adjacent masonry. So the intent is that the mortar is the sacrificial element to protect the masonry units. So it needs to be softer and more porous. In this image on the left, you can see evidence of many previous repointing campaigns at St. Joseph Shrine. In this image, some mortar is well adhered. Some mortar is visibly debonded and cracked. And some mortar just has a totally different color and aggregate composition than the others. The red arrow indicates the mortar that looks most similar to the original mortar, which is a sand lime mortar commonly referred to as lime putty. It's advantageous to match the properties of the original mortar for repairs and repointing projects. Mortar components and estimated proportions can be evaluated by petrographers and chemists when samples are extracted. So now that we've established some definitions and context around our bell tower project, let's talk about what's wrong with it. All building materials deteriorate over time. The mechanics for deterioration will continue until we address those underlying conditions, since buildings obviously cannot heal themselves. Here is a list of deterioration mechanisms that we commonly see in masonry structures. At St. Joseph, we have seen erosion and disintegration, cyclic freeze-thaw, corrosion, and one example of biological mechanisms. However, most of our deterioration has been related to erosion, disintegration, and corrosion. Erosion is the process of wearing away and transporting rock or sediment by natural agents like water, wind, ice, or even gravity. Disintegration of masonry refers to crumbling, flaking, or powdering of bricks, stone, or mortar, usually caused by moisture infiltration and freeze-thaw. The quality of the masonry units and mortar materials is fundamental to optimal performance of the wall. However, even high-quality masonry materials, such as those present at the original St. Joseph Church, are susceptible to deterioration, particularly when these materials are exposed to harsh environments for extended periods of time, which also includes harsh cleaning procedures. These photos demonstrate disintegration at some sandstone units along the bedding planes. These photos demonstrate erosion along the sandstone units as well as within the mortar joints. So in the photo on the right, you can see that the mortar is almost gone from within the joint. Cyclic freezing and thawing. Masonry wetting occurs as a result of water being absorbed from the environments, which can happen via rain, snow, ice, or even rising damp from groundwater. In certain regions, such as here in Detroit, absorbed moisture may experience freezing and thawing of varying frequency and severity. Water trapped in voids and cracks in the masonry units and mortar expand during freezing cycles, causing cracks and often rupturing the materials. If these voids are not addressed, future cracks and additional spalls may propagate throughout the wall, allowing additional moisture into the masonry where it can freeze and in turn expand the area of deterioration. Here we can see an example of open mortar joints as well as missing masonry units that may have been the result of freeze-thaw damage within the mortar. Ice lensing can also result in shifting and movement, which we have seen examples of at the bell tower, specifically in the corners. The red arrow on the screen identifies the top corner of this stone that is actually slightly out of plane with the stone above. This image shows some exposed brick masonry backup wall at the southeast corner of the bell tower. Generally, the brick backup wall has held up well over time. However, there have been a few localized brick masonry units with freeze-thaw damage. This is pretty readily identified with sounding with a hammer. The units are usually pretty soft and they flake apart easily when they're tapped. Okay, let's discuss corrosion a little bit. Steel components are commonly embedded throughout masonry walls in order to provide support to the masonry and to accommodate other architectural elements and openings. Corrosion of embedded steel can result in a buildup of compressive stress due to the accumulation of iron oxide, which is a phenomenon commonly referred to as rust jacking. For every unit volume of steel that corrodes, the corrosion product occupies roughly 4 to 10 times more volume than the original steel. The resulting compressive stress can cause out-of-plane displacement or bowing, cracks and spalls of masonry units and mortar. And additionally, corrosion results in reduced structural section that will reduce the structural capacity of that member. These are some historical examples of steel anchors, some of which we have observed at the bell tower. Here are a couple partially visible kerf anchors, similar to the ones seen on the previous slide. This image is looking down at the top surface of some sandstone units in the corner of the bell tower after the units above were removed. The kerfs turn down into the sandstone on their outside edge, extend back into the brick backup wall, and then actually turn up on the inside face of the inside wipe. Corrosion is initiated by the exposure of embedded steel components to water. Once the expansive forces create a crack in the masonry, additional water can infiltrate to the steel and then exacerbate that corrosion, leading to an accelerated process of deterioration. Exposure and building geometry can increase the potential for moisture infiltration. For example, steel components that are closer to the exterior face of the wall are going to be more prone to corrosion. Additionally, moisture penetration increases in really wet or high wind environments, and the bell tower is definitely in a high wind environment. Corrosion is particularly concerning at the bell tower finials, where these masonry elements are just less massive as they get more and more slender toward the top. These surfaces are more exposed, creating a higher risk for corrosion. At the finials, for example, moisture exposure is occurring on all sides. These elements are also set away from the building wall, and so they don't get the advantages of the protection associated with the building's more consistent temperature. And so as a result, these finials are also more prone to freeze-thaw cycles. And here is our one example of biological mechanisms. In the image on the left, we found this little plant in one of the joints between sandstone units at about 90 feet up in the air. And then later in the year, we were able to get into the wall actually and see that the roots really extended deep into the backup wall. So now that we understand some of the problems, how do we move forward and make improvements? As with any project on an existing building, many priorities are considered and balanced as decisions are made. Some of the key drivers related to this project are safety. This project began as a need to protect the community from potential fall hazards. So how do we address those hazards and do so safely? Budget. There's only so much funding available. How can we be creative with our work items? How can we keep the community informed and engaged? Preservation. You know, the struggle to apply the Secretary of the Interior standards in each of our decisions. And then technology and ingenuity. How can we use the tools, materials, and technology available to be most effective with our work? This is where we can really flex to try and check the boxes listed above, but it doesn't always work. I just want to go through briefly the Secretary of the Interior standards for the treatment of historic properties to consider. Preservation. Preservation focuses on sustaining the existing form, integrity, and materials. One thing I really appreciate about this definition is that simple maintenance is recognized as preservation. Rehabilitation. Rehabilitation focuses on preserving features which convey the original historical, cultural, or architectural values. Restoration. Restoration focuses on bringing something back to what it once was, while also acknowledging that sensitive upgrades may be necessary or even required. And then reconstruction. Reconstruction focuses on replication with new materials to bring something back to its appearance at a specific time period in the past. Okay, safety. This project began as a result of fall hazards observed at the bell tower, which unfortunately were located directly above the main entrances and pedestrian walkways. And the bell tower finials were of particular concern during our initial survey, as you can see here. Church occupancy. All of our work has continued while this very, very busy church is fully functioning. How do we keep this community safe while performing our work? Here you can see a couple photos of community gatherings with our equipment and our project going on in the background. One thing we did was recommend overhead protection at highly trafficked areas such as the entrances and busy sidewalks. The overhead protection also pushes people further away from or as far away from the building as we can. We're also using barricades at our staging areas, and we frequently shut down streets and parking lots temporarily as we move equipment and store materials. This bell tower is also difficult to access. The masonry at the bell tower extends almost 150 feet up in the air from grade, which has a big impact on budget. There are no existing designated tie-off points, roof access, or other ways to inspect or repair exterior enclosure components without expensive equipment. Um, this difficult access also creates issues for maintenance and inspection moving forward and during the service life of these materials. And remember, if we think back to our discussion about mass masonry walls, one of the primary methods of protecting against water infiltration is deflection of water at the exterior surfaces. These exposed masonry elements are our primary defenders against moisture-related deterioration. But also consider like the glazing and sealants at the windows, paint and wood at the louvers, and slate and metal flashings at the roof. It adds up very, very quickly. So access for repairs significantly impacts the cost of any work that we perform. Methods of access so far that we've used include drone survey, interior just visual survey. We've used an aerial lift, crane basket, mass scaffolding, swing stage, and even a little bit of rappelling. WJE began with assessments from afar, including drone and aerial lift access. These helped us to develop repair drawings and helped limit expensive access mobilization multiple times. We were able to estimate quantities and locations of repairs and then also develop our drawings, a snip of which you can see on the right. Once our mass scaffold was in place, we had up-close hands-on access, and we were able to perform some investigative openings at key locations. We performed sounding surveys to evaluate the integrity of the existing stone, and we've been marking up repairs directly onto the facade. The contractor, like I said, has helped us perform inspection openings at key locations that we selected to help us uncover embedded elements, which help us better understand the original construction intent. This allows us to reconstruct and preserve as much as possible without compromising the structural and watertight integrity of the enclosure systems. We're also using a proprietary software to communicate with the church and the contractor during the project. So these like living documents are real-time updates of repairs that we identify on the building. In keeping with the maintenance and preservation thoughts, part of our project includes repointing mortar within joints, particularly at these upper levels, which are particularly difficult to access. With the help of our petrographers, we performed mortar analysis during our original assessment and determined the original mortar to be a lime putty composition. We're installing the same mortar type within these joints as part of our repair effort. Here you can see some snips of the lime putty curing process. After the mortar is installed, protective burlap is hung and then misted with water in regular intervals. Once the mortar goes through at least 9 cycles of wetting and drying, the burlap can be removed. And then we'll review and repair the mortar as needed as part of the punch list to address any cracks or separation that may have occurred, which indicates issues with the curing process. And as you can imagine, pumping water up 100 feet into the air and protecting this mortar from wind was not easy. These masons have been doing a great job and are very attentive to detail. Now let's dive into some of the more nuanced work related to the stone. As part of our up-close assessment, we performed a sounding survey to evaluate the integrity of the existing stones, including the dolomite limestone. Simultaneously, the contractor was performing localized mortar and stone removal in preparation for repointing and miscellaneous stone replacements. And so as a result, more of the dolomite was available for us to review, exposing the bedding plane orientation. Most, if not all, of the original dolomite limestone was set with a vertical bedding plane or face bed. In the image here, you can see the cracks extending in the up and down direction on both of these dolomite units. Unfortunately, our sounding survey revealed a large number of unsound dolomite units. Many incipient spalls were simply removed by hand, and then many incipient spalls also fell out during mortar removal. And if we go back to the original intent of our project, removing hazards is our highest priority. So how do we balance this safety mindset with budget and preservation? Our initial approach was to use an epoxy adhesive to try and re-secure these loose fragments in place. So the contractor installed mock-ups with the salvageable fragments that fit within certain thicknesses. However, the viscosity of the epoxy was too thin to allow for full bedding of these fragments, and so the mock-ups wound up being unsound when we reviewed even after sufficient cure times. Our second approach included pinning units in place with adhesive anchors set at downward and inward angles. This allowed gravity to work in conjunction with the adhesive and mechanical connection to hold stone fragments in place. We used thin threaded rods set in adhesive with stainless steel screens to secure these unsound dolomite units. The existing stones that were partially missing and left exposed horizontal surfaces for moisture accumulation were ultimately replaced. Replacement stones are being set in full collar joints to maintain that continuity of the mass masonry wall. We were able to salvage many dolomite units, even those that had some missing spalls. Units with removed spalls that did not create that exposed horizontal surface for moisture accumulation were ultimately left in place. Similar to our dolomite survey, the sandstone units on the bell tower were reviewed up close and sounded. Typical work items included removing loose material, mortar patches, Dutchman, sealing cracks, removing and resetting existing stones, repairing broken stones, replacing stones, and recreating some missing stones. Here's a simple example of just removing loose material. The project team has been really thoughtful about this approach. We consider location and visibility from grade and pay special attention to the most visible facades. We also ensure that any removed material is not creating some obvious potential path for water infiltration or future accelerated deterioration. Here's an example of both repairing a broken stone and a mortar patch. You can see here how one of the corner decorative pieces broke off from the main part of this finial stone. On the left, you can see our little detail sketch of the proposed repair. And then on the right, you can see sample mortar patch materials for color selection. Here's an in-progress photo of that repair. And then the completed repair. And ultimately, this stone will be reinstalled. Here's an example of a finial stone that will be replaced. Anchor corrosion was present both at the top and bottom of this stone. And the force from expansion was so great that the stone actually just split vertically in two. These guys didn't even need materials to disassemble this stone. Unfortunately, in combination with other deterioration happening, the stone is not going to be salvaged and will be replicated. Here are some images of the masons removing stones that are scheduled to just be reset. This approach is being used at stones which were displaced from the backup wall, had voids within the collar joints, were no longer plumb, or were laid in such a way that they couldn't safely be shored in place during repairs in other nearby locations. Here are some photos of an in-progress partial depth Dutchman repair, which is at one of the large finial bases. Here's a before photo from our sounding survey. Delamination was found within the outer few inches of this sandstone. And in these photos, you can see that delamination along the bedding plane in the vertical direction. This also sounds hollow when you tap it with a hammer, and in some cases, it even vibrates a bit as well. You can also see in this photo that the stone that was further into the wall, so like to the right of the arrows, is sound. We don't see that delamination. And the mason was able to carefully remove the unsound material without damaging that inner portion of the existing stone. Just in case not everyone is aware, a stone Dutchman is a repair technique in which a damaged or deteriorated section of stone is removed and replaced with a new matching piece of stone. The repair can include the full depth of the original stone, like on the right, or a partial depth, so like what we're talking about and on the left. The new piece of stone is secured with mortar, epoxy, and then stainless steel pins and straps. So to maintain the mass masonry wall, the contractor filled the collar joint with mortar before setting the new Dutchman onto multiple stainless steel straps and pins, like we saw in the previous details. This detail is not easy to execute, and I equate this to trying to thread a needle while holding a few 100 pounds. These guys did a great job, but this repair approach allows us to reduce costs by avoiding replacement, preserve as much of the original material as possible, and still maintain the continuity of the masonry cross-section. At a couple locations where the stones are scheduled to be replaced, we run into an interesting issue relating to bedding planes and production sizes. Berea sandstone is being sourced from Cleveland quarries, and they have dimension restrictions because of mining equipment and technology. The mason is working really closely with the stone supplier to scan the existing stone units in place and then also at the staging area to confirm sizes. And some stone units require dimensions that are larger than what is able to be quarried, meaning that we're unable to replicate the stones in the required dimensions with those horizontal bedding planes that we want. So the project team was able to consider a few different alternatives for this problem. First of all, we could just remove and replace the stone in like kind. We considered that many of the existing stones were not only installed with vertical bedding planes, but they also had a service life of 150 years with corroded embedded elements. And this was our cheapest option. Another option was to change the joint layout. So rather than making one large stone, we could install two smaller stones and add an extra bed joint. This way we could achieve the improved durability with our horizontal bedding planes. However, there was a slightly higher cost associated with extra labor and materials with that additional new bed joint. And it also impacts the appearance of the original installation. Our third option was to fabricate a new stone with an epoxy joint to achieve the dimension needed with the desired bedding plane orientation. So this improves the durability of the stone, incorporates modern epoxy adhesives to maintain the original joint layout, but it's also the most expensive option. You can see images on the screen now that show the mock-up of this option. In the center photo, you can see the epoxy joint with my finger. It's almost indiscernible, especially when it's hung up on the bell tower. But ultimately, the owner reviewed the mock-ups and decided to proceed with option one. So they proceeded with removing and replacing in like kind. The final work item I would like to discuss is a new kind of exciting development related to these large gables on the east, north, and west facades. On the skyward facing surfaces of these gable units, there were originally very ornate carved stone elements that were set in a mortise and tenon joint. Unfortunately, only 4 of the original 42 remain. Here you can see one of the few we observed in place and one of the many open mortise pockets. In some locations, the tenon actually sheared off of the decorative part of the stone, and that remains in the mortise pocket. Our project team considered installing mortar patch material in the open pockets, just in an effort to minimize the collection of moisture and promote positive drainage away from the wall. Alternatively, the church could consider recreating these original decorative ornamentation pieces. And after thoughtful consideration, the church has recently decided to recreate the original ornate decoration on all 3 facades. As part of this new installation, our team intends to develop a detail that enhances the long-term durability of this mortise and tenon connection by incorporating mechanical anchorage and adhesives. This reconstruction effort is really going to enhance the appearance of the bell tower and go a long way to reestablishing this beautiful structure to its original design. And we've come to the end. So to summarize, we've discussed church history, basics of mass masonry construction, masonry materials, methods of deterioration, some preservation principles, and some example repairs. This has been one of my favorite projects, and I'm so grateful for the opportunity to be part of this project team. We're looking forward to continue being stewards of this beautiful building. So keep an eye out for us this summer as we continue to put the beacon of hope back together. And thank you so much for listening.
Thank you, Julie. Thank you for the wonderful presentation and all the details that you shared with us. This is very amazing project, and we do have quite a few questions in the Q&A. Let's get started with that. First question, what was the total budget for this project? Were both public and private resources made available to support it?
Um, from what I know, I don't have the total project budget memorized, but from what I know, the project has been funded by donations from the community. A very enthusiastic, supportive community. It's incredible.
Oh, wow. That's amazing. Okay, next question. So what was the quality of the materials used to build the church in the first place? How well was it built?
I think the fact that this church has been in place since 1873 um, and has lasted this long, even though it kind of fell into disrepair when the population and the community decreased in size, is really a testament to the quality of the original construction. The actual materials used were very high quality, very appropriate for their installation. Um, so it was a very high quality advanced building at the time. I think when it was completed, it was the tallest building in the city.
Oh, wow. Okay, next question. With standard width cavities built into the mass masonry walls, do they become irregular as the building settles? What kind of issues that um will that cause?
So we don't have open cavities. We've uncovered some deteriorated mortar within the backup wall, which will be repointing. And we haven't really seen signs of settlement in this building either. Um, Mass masonry structures are a little bit more susceptible to wind and earthquake movement. So there are some cracks inside, but we haven't seen any movement of the cracks over the last few years. So the building is generally very sound.
Okay, thank you. Next question. Prior to this current restoration, and I think besides the repointing that you mentioned in your presentation, had the church undertake any ill-conceived restoration efforts that you had to reverse?
We have not reversed anything. No, no, I wasn't involved in every project that the church took on, but they have undertaken a lot that has gone a long way to improve the long-term durability. I know back in 2016, right when the canons came to the church and became involved in the community, there was a wind event that damaged the roof structure of the steeple. So right from the get-go, they were solving building problems. Um, and it's gone a long way to improving and preserving the building for the future.
Okay. Next question. How did you find working with the city and its building department in proceeding with this project?
We've had no issues with the city. Um, WJE does not pull permits, so as the engineer of record, we don't really interact with the city on a day-to-day basis. Um, but we've had no issues with the city. I hope the city is embracing what we're doing because it's really a jewel on the skyline.
Next question. When you were exploring the bell tower, did you find any interesting graffiti, things left behind by the workers, dates, etc.?
Oh, yes. Yes, there's a roster of people in the bell tower. I think one of the earliest names is from 1912, maybe. And then there's some from the 60s, from the 70s, from the 2000s. Yeah.
Hmm.
It's
Wow.
all, yes, it's just a yearbook kind of.
Oh, wow. Cool. Okay. Next question. Um, Sorry, I'm trying to go back. How was the project site secured when the workday was over to keep people from exploring?
There are there's a staging area set up in the parking lot, which is protected with barricades. The guys on site also have a trailer. Um, and then the actual like sidewalk and overhead protection barricades access to the mass scaffolding access. Um, so lots of barricades, and the parish has had to work around them for, you know, quite a while. They're very patient.
Okay, thank you. Next question. Did the church stay on top of maintenance over the decades, or was there damage that could have been avoided in the first place?
Maintenance on these structures, I talked about this a little bit, is difficult, particularly where we're working right now. We're 150 feet up in the air, and there's no inexpensive, easy way to get to it. So maintenance is going to be a long-term issue to consider moving forward. So regular inspection is helpful, but is difficult. Um, so yeah, it's just an inherent part of the way this building is constructed.
Okay, thank you. Next question. Were repairs to the copper detailing and wood belfry screen being executed at the same time, or are those scheduled for the future?
So we are only getting into the copper in a very small area at the upper finials, in some locations. So there is a copper apron flashing at the base of the slate steeple roof that obviously ties in a watertight fashion to the finials. So when those finials have work items, we're opening up the copper flashing and we'll have to, tie it back together. And then at the belfry level, I didn't get into any of the louver or window discussion as part of this presentation, but at one of the louvers, we did uncover some wood deterioration, which we are just finishing, actually. I think yesterday they finished. So there's been very limited wood restoration, but we have done some at the exposed portions of the louvers, and we'll be doing some at the exposed portions of the windows as well.
Mhm.
But yeah, I didn't talk about that much. This was masonry mostly.
Okay, next question. So Melissa said, our board president said, outstanding work. And what was a part about the project that could have gone better? Or did you have any hard calls or project decisions that you wished were different?
I think I talked about the most difficult parts. As an engineer and as, this project kind of kicked off as a safety issue, um, we were able to understand the dolomite and the sandstone as surrounding elements like the mortar was removed, but then we were also made more aware of some of the unsafe conditions. And so that wound up being more than we originally anticipated, which is always difficult to, figure out and talk with the owner about. So that spurred us to try and come up with ways to make still safe but less costly repairs to help try and save the community some money while still achieving their goal of safety. So that was probably the most difficult thing.
Okay. I think we have one last question.
Sure.
What kind of celebration is being planned by the church when this project is done? And is it something that as a public can access? Get a tour of the building?
That's a great last question. And I don't know. That would be up to the canons, I guess. But they post very frequent, great updates on their social media. We, text them photos while we're up on the bell tower that they share with the community. So they're very engaged with keeping the community informed. So if you find their social media, I'm sure you can learn about what celebrations are upcoming because we need one.
Mhm. Well, if we find out, we will let everybody know.
Sounds good.
Um,
Yeah, we can do that.
Okay, well, I think that's all the questions. And thank you again, Julie, for your presentation. We got a lot of comments from the audience that this is a terrific, well-organized presentation, and
Oh,
everybody
thank you.
enjoyed it. And thank you for everyone to spend the hour with us. And this webinar is being recorded. The recording will be available in the next few days. You will receive an email when it is available. And when this webinar closed down, you will see a survey that will pop up on your screen, and please participate in the survey to help us improve our program. And our next webinar is yet to be announced. You will receive an email when it is when the registration is open. And our conference is next week in Detroit. Hope to see a lot of you there. And so follow our website, Facebook, and LinkedIn for our future events. And I hope to see you all next time. Thank you.
Thank you.